Welcome back, guys, to another video. Here we'll break down the Henderson Hasselbalch equation and go through 5 practice problems step by step. Let's get to it. First thing to discuss about the Henderson Hasselbalch equation is this variable called the pKa. Just like how the P in pH represents the negative log of the H plus concentration, the P in pKa represents the negative log of the Ka. The Ka is a dissociation constant, which we talked about in the last video. If you guys haven't seen that video, I'll leave the link to it right over here.
So let's do an example. At equilibrium, a buffer mixture was found to have 0.04 moles of dissolved NaF and 2.2 moles of HF in 1 liter of solution. Determine the Ka and pKa. So we know in a buffer mixture we have HA and A-. For these two fluorine molecules, the one bonded with the hydrogen is our HA and the other one is our A-. That's because in water, this molecule completely dissolves into Na+, and more importantly, the F-, which explains why this is our A-. So first step is to write out our Ka equation. We know that for every dissolved HA, there is an equal number of A- as H+. So we can rewrite the equation to look like this. And since we know A- is NaF, we'll plug its value in, and we know HF is our HA. Once we do this, we get our Ka value. To get to pKa, we'll just take its negative log, and this gets us our answer.
So let's talk about the Henderson-Hasselbalch equation. It tells us the pH of a weak acid, given its pKa, and the concentrations of its conjugate base and weak acid form, known as the buffer.
So let's do a problem. The pKa of a weak acid is 5.0. Calculate the pH of a solution composed of 0.04 molar weak acid and 0.02 conjugate base. We know our weak acid is our HA, and the conjugate base is our A-. We know the pKa of the weak acid. With all these variables, we know to use the HH equation. So we'll put that in, and next we'll plug in our variables. Our pKa is 5, our A- is 0.02, and our HA is 0.04. Once we do this, we get us our answer. So let's do another problem. Determine the mass of NaF in grams that must be added to 40.5 milliliters of 0.3 molar HF solution for a pH of 3.5. The Ka is given to us. So first things first, we know HF is our HA. NaF, which is the same as F-, is our A-. We also know our pH and Ka. So we have all the pieces set for the HH equation. We'll plug in our value for pH, and for pKa, we know it's equivalent to the negative log of Ka, which once we plug in our value, we get this value for pKa. Next, it's important to note that the A- and HA in the HH equation is in the units of molars. So for HA, that value is 0.3. Now, let's solve for the molars of A-. First, we'll move the 3.14 over. Next, take out log with a base 10. And when we multiply 2.29 on both sides, we get this value. And again, this is in the units of molars, aka moles per liter. So how can we convert its units to grams? First, let's take out its liters, since we know the volume. Convert the milliliter in the problem to liters. Next, we'll multiply these values together and get us our moles. From here, we can easily get to grams by using the molar mass of NaF. This gets us our final answer of 1.18 grams of NaF. Before we move on to the next portion, if you haven't liked the video or subscribed to the channel yet, please do so. Also join me at nicoscience.com. Here you can find my tutoring website where you can book a session in this button below and choose from a range of subjects from biochemistry, physiology, biology, chemistry, and genetics. All right, back to the video. Given pH of a 0.05 molar solution of an acid is 4.3, determine its pKa. So we know the pH and the pKa in this problem. So do we use the HH equation here? Well, we don't know our A minus or pKa, so in this case we won't. Let's use something else. We can try to use the pH equation to find the H+. Since we know that for every H+, there's an A-, we can plug it into the Ka equation and find pKa. So we know our pH is 4.3. Next, let's isolate H+, which gets us this value for the H+ concentration. Next, let's write out the Ka equation. Again, we know for every H+, there's an A-. This is a common trend whenever we're dealing with pH problems. So we can rewrite the equation like this and plug in our value. Next, we'll put in our HA value from the problem, and this gets us this value for Ka. From here, all we have to do is take its negative log, and when we do so, we get our final answer of 7.3. 0.45 grams of weak acid was placed in 2 liters of water. Determine the pH of the solution. The pKa and molecular weight is given to us in the problem. Here we have grams of weak acid, the pKa, and we need to find the pH. Using the molecular weight, we can convert the grams to moles, and we can divide this by the volume to get us our molars. So let's do that. First, with our grams of weak acid, we'll set up the stoichiometry table to look like this. And this gets us the concentration of the weak acid. Next, for the HH equation, we know our pKa, but that's about it. So let's use a Ka equation like we did before. And again, it can be simplified like this. Next, let's plug in the HA we got from earlier. And now let's find the Ka by using the pKa equation, which we know equals to 4.8. So we'll isolate for Ka like we did last problem. Take out the log by the base 10 on both sides, and we get this value for our Ka. So we'll plug this value into the blue equation, and from here we'll solve for H+, which gets us this many molars. Finally, we'll take the negative log of this value to get us our pH. And when we do so, we get the final pH value of 1.19.